This is a continuation of section 4.1 about basic probabilities. We studied what we mean by mutually exclusive events. We said that mutually exclusive events are events in which there is no intersection between them. There is no overlapping, no intersection. What about independent and dependent events? Two events are independent if the occurrence of one event is no way influences the probability of the occurrence of the other event. You need to understand the definition carefully. I have two events. The occurrence of one of them does not influence the probability of the occurrence of the other. For example, if I ask you, what is the probability that you come to the class on Thursday, and you say it is zero point 0.7, that's okay. This is the probability of an event, which is you coming to the class on Thursday. You said zero point 0.7. Now I ask you, what is the probability that you come to the class on Thursday if you have to go somewhere with your friends, for example? If your friends invited you to travel to Dammam or anywhere. Now, if you say the probability that I come on Thursday would be also zero point 0.7, it means you did not change the probability, although your friends are going to Dammam. Then this means that the event that your friends going to Dammam and the event that you are coming to the class are independent of each other. They do not influence each other. But if you say to me, oh, in this case, the probability would be 0.4, so the probability changed from zero point 0.7 to 0.4 because of the event that your friends are going to Dammam, then these two probabilities, these two events are not independent. You need to understand the definition as it is. While the dependent events, two events are dependent if the occurrence of one event impacts and influences the probability of the other event. This is the definition of independent and dependent events. So we cannot discuss, for example, I mean, whether two mutually exclusive are dependent or independent. This is a definition and this is another definition. Two mutually exclusive could be dependent or could be independent. We will see that later, okay? Let us solve this exercise. You toss a fair coin in the air and then draw a card from a deck of 52 cards. So let us understand the experiment here. The experiment here consists of two actions. First, you will toss a fair coin, and then you draw a card. If we are asked to find the sample space of this experiment, you can draw a tree diagram. When you toss a coin, you will get either head or tail. He did not ask about the sample space, but I am just reviewing the concept of the sample space. You need to understand the experiment in each question about probability. Now, this is what he does first, and then you draw a card from a deck of 52. When you draw a card of 52, you will have 52 possibilities. Okay, 52 possibilities. So, how many elements in the sample space? 2 for the first choice times 52 in the second choice. This is the number of elements in sample space. Anyway, this is not the question. The question is, will the probability of drawing a king from the deck be affected by the output of the coin toss? So we have two events now. First one, drawing a king. The second one, uh, the coin toss, the result or the output of the coin toss. So if you toss a head or if you toss a tail, will this change or influence the probability that you draw a king from the deck of the 52 cards? And I think you will just say, of course, no, it doesn't influence. This is something and this is something else. No, there is no influence. It doesn't affect. Okay. So what what does this mean? It means that these two events are independent. So the two events, what are the two events? The first one drawing a king, and the second one uh, the output of the coin toss. The two events are independent, independent from each other because the occurrence of the first one does not change the probability of the second one. By the way, we will define now how can we find the probability of drawing a king from the deck of 52 cards. You can think of that. What is the probability of drawing a king from a deck of 52 cards? There are two methods to uh, assign or to compute probabilities. The first one is called classical probability assessment. And this method, the method of determining probability based on the ratio of the number of ways an outcome or event of interest can occur to the number of ways any outcome or event can occur when the individual outcomes are equally likely. It's important, very important here, that the outcomes are equally likely. And equally likely means each outcome has the same probability or the same chance to happen. So, for example, uh, drawing a card from the 52 cards is an equally likely experiment because each card has the same chance to be picked. When you toss a coin, a fair coin, an equally likely experiment. When you roll a die, this is an equally likely experiment because getting 1 to 6, all of them have the same chance to happen. But when you have equally likely outcomes, you use classical probability. In fact, you can also mention that when there is no experiment or no trials, okay, let me say no trials or no experiment happened. So, for example, here, uh, picking or choose a king or draw a king from 52 cards. Now, how to find the probability of a king? Let me call it K. It is a ratio, number of ways an outcome or event of interest can occur. What is the event of interest here? It is drawing a king. So, how many kings are there in the 52 cards? This is the number of ways an outcome of or event of interest can occur. How many kings are there? You should know, or if you know, there are 4 kings in the 52 cards. So this is the number of ways event of interest can occur. We divide that by the number of ways any outcome can occur. So all outcomes, all cards. Of course, each outcome here is a card because you pick one card. Each outcome is one card. For how many cards are there? We have 52 cards. So this is the probability of drawing a king from 52 cards using classical probability. Notice we did not, no trials here. I mean, we did not do this experiment really. We did not pick a card. Okay? No experiment. Nothing happened. We are just asking if there is a deck of 52 cards, what would be the probability of drawing a king? If the question is like this, you use the classical probability. We did not do anything. We did not do any experiments. We did not really pick kings. Okay? So this is the classical probability. Let us take some examples. As I told you, tossing a coin is one example, and of course it is equally likely, and we have two possible outcomes flipping a coin, but it has to be fair coin. It has to be a fair coin. So for example, what is the probability of tossing a head? We have two outcomes, head or tail, and number of heads in the two outcomes is 1. So 1 over 2. Probability of head is 1 over 2, and probability of tail is also 1 over 2. So this is the classical probability, number of ways the event can occur over the total number of possible outcomes. Another example about classical probability. The managers at King's Fine Clothes plan to hold a special promotion over Labor Day weekend. Each customer who makes a purchase exceeding $100 will qualify to select an envelope from a large drum. So if you buy with more than 100 exceeding, you will select an envelope. Inside the envelope are coupons for percentage discounts of the purchase total. At the beginning of the weekend, at the beginning of the weekend, so nobody yet bought anything or picked any envelope. At the beginning of the weekend, there were 500 coupons. 400 of these were for a 10% discount. 50 were for 20%, 45 for 30%, 5 were for 50%. So he is illustrating the kind of coupons there. Some coupons with 50% discount, 30%, 20%, 10%. Of course, the majority are 10% discount. Nobody yet picked any envelope. The probability of getting a particular discount amount, yeah, okay. Before any experiment could happen, before any trial, we can ask, what is the probability of selecting whatever 10% discount? We will see his question. What would be the question? What is the experiment? We select an envelope from a large drum. Okay, what would you get? Of course, would you get an envelope? And each envelope has a different discount amount. Some of them are the same. Okay, and they are mixed in the drum. So each envelope has the same probability to be picked like the other envelope. All the 500 envelopes have the same probability to be picked. So you can say that this experiment is equally likely. All the outcomes are equally likely. Now, the total number of outcomes, we have 500 envelopes. If you are searching for 20% discount, okay, we might be interested in assessing the probability. So this is the question now. What is the probability that the first customer will get a 20% discount? He did not pick, but this is a hypothetical question. What is the probability that the first customer will get a 20% discount? How to answer this? You use classical probability. How many envelopes with 20% discount? 50 coupons, 50 envelopes, and the total number of envelopes is 500. So you divide 50 over 500, and the probability of obtaining a 20% discount would be zero point 0.1. Note, after the first customer removes an envelope from the drum, the probability of the next customer will change, will be different. Yani, the probability that the first customer obtains 20% would be zero point 0.1. But the probability that the second customer obtains 20% would be changed because it depends on whether the first customer obtained 20% or not. Okay. If he obtained 20% discount, then the number of 20% discount envelopes would be 49. So the probability of the second customer would be 49 over 499. But if he does not obtain a 20% discount, the first customer, he obtained some other discount, then the probability that the second customer obtaining 20% discount would be 50 because the 50 did not change over 499. So for the next customer, for the second customer, his probability could be 49 over 499 or 50 over 499. Another question, students who live on campus and purchase a meal plan are randomly assigned to one of three dining halls. So there are three dining halls: Commons, Northeast, and Fraser. Three uh, dining halls, C, N, and F, let us say. What is the probability that the next student to purchase a meal plan will be assigned to C or Commons? Notice here, he did not ask in this question about the sample space. Okay, he is asking about the probability. What is the probability? Uh, Nobody yet. Okay, the next student, the student did not go yet. So what is the probability that the next student will be assigned to one of these three halls? These are three halls, so the probability would be he will be assigned to one hall. So number one hall would be 1, and three halls would be 3. So the probability would be probability of this event would be 1 over 3, simply 1 over 3. If you are talking about sample space here, sample space would be NFC, 3 possibilities in the sample space. So the probability of C would be 1 over 3, which is the total outcomes, the number of all dining halls. Another exercise, company with 10 employees. Those 10 employees, 7 of them are females and 3 are males. Assess the probability of a female employee being selected. So the question, what is the probability that we select a female at random to travel to a convention? So what is the probability of selecting one female from 10 employees? That's the question. So probability of F, if F refers to females, would be, according to classical method, number of females, how many females are there, over the total number of employees, it would be 7 over 10. New car dealer has 5 GM, 6 Ford, 3 Toyota, 8 Nissan, 2 BMW cars. If one car is selected to be placed on sale, what is the probability that it is a Nissan? So this is the event. One car is selected to be placed on a sale. Let me call it E. The question, what is the probability of this event? Okay. Total number of cars of event, total outcomes, we will select one car. So each car is an outcome. What is the total number of cars? 11, 14, 28, 24. We need to select a Nissan. What is the probability of selecting a Nissan? How many Nissans are there? 8. So the probability is 8 over 24. All of these questions were questions about classical probability assessment. Let us now talk about relative frequency assessment. Here there is an experiment. Okay, there are trials. We did the experiment many times. Experiment. Relative frequency assessment, the method that defines probability as the number of times an event occurs divided by the total number of times an experiment is performed in a large number of trials. So there is an experiment here, and the outcomes need not be equally likely. In all of these questions, all the outcomes were equally likely. For example, in the last exercise, any car would have been selected. So they have the same chance to be selected. But now, in the relative frequency assessment, no, they are not equally likely. And there is an experiment. So number of times the event occur, always number of times the event occur over the total number of times an experiment can occur. Let us see an exercise. This is a table. We have two variables, heating systems, or two events here, heating systems, air conditioning systems. This is E3, E4. And another two events here, E1 commercial and residential, E2. Of course, there are two variables, okay? One variable, customer category, which could be commercial or residential. And this is the Hathaway heating. We have two types, heating systems or air conditioning systems. And we have some numbers inside the table. So 55, for example, says that there are 55 commercial heating systems. Okay, 145, there are 145 heating systems residential. If you want to read the question, the sales manager at Hathaway Heating and Air Conditioning has recently developed the customer profile shown in this table. The profile is based on Hathaway's 500 customers. So these are number of customers, and the total number of customers is 500. As a promotion for the company, the sales manager plans to randomly select a customer once a month and perform a free service on the customer system. What is the probability that the first customer selected is a residential customer? So he needs the probability that the first customer selected is a residential customer. Notice here that this table, from where we got these numbers, an experiment had happened. Okay, we have seen before that among the 500 customers, 55 of them were commercial and used heating systems. Okay, for this is an experiment happened, and these are trials. 500 times we saw each customer, what is his category and what system he chose. Okay, so uh, we use relative frequency, and relative frequency, if you remember, the frequency over the total number. So the total number is 500, and he is asking about probability of residential. Okay, where is residential? This is residential. 145 residential. He used his heating systems. 255 is also residential, used air conditioning systems. So we add these two, we get 400. So we have 400 residential over the total, which is 500. So the probability of residential would be 400 over 500, or 0.8. So there is an 80% chance the customer selected will be a residential customer. He is also asked, what is the probability that the first customer has a Hathaway heating system? Heating system, this is the heating system. So the 55 heating systems and 145 are also heating systems. So we add them, the total would be 200. So the probability of heating systems, okay, would be 200 over the total number, which is 500, and this will give you zero point 0.4. So there are 40%, or there is 30% chance to randomly select that the randomly selected customer will have a Hathaway heating system. Notice that we can find the intersection probability. Okay, so here he is asking residential with heating. Okay, the sales manager hopes the customer selected is a residential customer with either way heating system. So residential with heating. So if you look to the table, 145 are residential with heating systems. So the probability of residential intersection heating systems would be 145 over the total number, which is again 500, and it would be 0.29. Another example, the results of census of 2,500 employees of a mid-sized company with 401k retirement accounts are as follows. Here you have the account balance. This is the first variable. There are four choices, and the gender, male or female. It is also a form of table, and he will ask you, based on the relative frequency assessment method, what is the probability that randomly selected. There is something missing here. So let us answer part B. Based on the relative frequency assessment method, what's the probability that a randomly selected employee will have a 401k account balance between 250,000 and 49,000? So where is this between 250 and 49? It is this one. So we need to add 185 plus to 110 to get the total number of employees, and the total number would be 395. And we also need to find the total. Did he mention? Yeah, he said 2,500. So if you add all of these numbers, you should get 2,500. So the probability the account would be between this is probability of this event would be 395 over 2,500, which is the total number of employee. You can also ask about compute the probability that a randomly selected employee will be a female with an account balance between 50,000 and 99. So there are two things here. It should be a female, so we look to females only, and the balance is between 50 and 99, so it is 260. This is an intersection between females and the balance. So the probability of this event or female intersection, okay, intersection, if you can call them E1, E2, E3, or I just say it as E, both of them would be 260, the number of females with this balance over the total number of employee. This is again another table, so please you can read it and solve it. You need to find the totals here, the totals here, and you see, for example, probability that the mountain bike is brown. So you add all the browns and divide by the total. Probability YZ99, you add all YZ99 and divide by the total. Probability that is YZ99 and brown, so it would be 205 over the total, and so on. Let us see part D. Suppose a mountain bike is chosen at random. Consider the following two events. The event that the model YZ99 is chosen. So that's the first event. YZ99 is chosen. Okay. What is the second? The event that a white product is chosen. Where is the white product? This is the white product. So one event white, second event YZ99. What is the question? Are these two events mutually exclusive? If you understand mutually exclusive, you will say immediately no and explain because since there is an intersection, they intersect. How? There are 130 white and YZ99 intersection. There is an intersection between the two events. So it is not, these two events are not mutually exclusive. The probability of their intersection, white and YZ99, is not zero. For the mutually exclusive, the probability should be zero. The probability here is 130 over the total number of bikes. You need to count all of them, find the total, and put it here. So very simple. They are not mutually exclusive because there is an intersection between the two events. I stop here and I open the floor for questions. Please, if you have any question,